The purpose of this video is to, more than introduce the concept of derivative, to recall the idea of the derivative. So the derivative is, in a nutshell, it's the slope of the line tangent to a function at a given value of x. So for instance, in this sketch of the function f of x equals x squared, the illustration here shows us a tangent line to the curve at some location. Now it turns out this is at about 1.5. X equals 1.5 down here, and we can see that this black line, its slope is exactly the same as the slope at that destination, at that location. So if we imagine for a moment that this is a roller coaster, and that we would travel on this roller coaster from left to right, maybe we're looking at the roller coaster. It gets kind of sketchy down here depending on the cart length, but once we get to about here, we can interpret the derivative and say that the significance of this idea of the instantaneous rate of change is if you were sitting in this cart at this point right here, we'll just pretend that this individual is sitting, the slope of this black line would indicate the incline at which you are facing at that instant along the ride. Now, one of the things that we know, of course, is the second we move, let's say we move here, well, that's the slope of that tangent line, as we can definitely see, it's going to be much steeper because we can see this curve is rapidly increasing in height. And so from a sort of conceptual standpoint, it would tell us in this case the direction in which we are facing, or really the measurement of the incline of that ride. Okay, and so there are lots of different applications that we would use for this. Again, here we're just sort of thinking about that this is horizontal distance that we're looking at horizontally, or I guess this would be, vertical distance or elevation versus horizontal distance. And if these were both measured in, say, feet, then if we calculated the rate of change right there, which we would write as f prime of 1.5, that's the slope. This stands for the instantaneous rate of change, which, again, I'll just abbreviate that so I don't have to keep on saying it, writing it out. And the slope at that point would actually be 3. Okay, so we'll come back to that. But what does it mean for the instantaneous rate of change to be 3? Well, given that we have units for this, I'm going to put this quantity over 1. Since it's a slope, it's a rate of change, I now have something to compare what we would often call the rise and the run, right? So in this case, the rise, it's literally a rise because the ride is moving upwards. It would be horizontal feet, or I'm sorry, vertical feet per horizontal foot, or feet of elevation per horizontal foot. So that essentially means that at that instant, based on where we're facing, if we went over 1 unit, okay, if we went over 1 foot, we would expect that the change in height would be 3 units. So basically 1, 2, and 3. And you can kind of see that this line would, if it continued going at the same rate, I didn't do this very much justice, but oh, I'm sorry, here we are at 3. So it would actually be a little bit higher. It would be about up there, right? And that would be, hypothetically, if we continued traveling at that same rise to run ratio, then we would increase our horizontal distance of 1, and we would increase our vertical distance by 3 feet. Okay, so that's one way we might be able to visualize what's going on here. Now, more than just telling us in the context of a problem what the slope is at a point, oftentimes, and especially in applications of computer science or gradient descent, different types of artificial intelligence, machine learning contexts. We're more interested in using the derivative to tell us or help us determine for what input values or x values the slopes are 0. Okay, so yeah, we can plug in a value of x and figure out what the slope is at that value of x on the curve, but we could also use the derivative function and set it equal to 0 and figure out for what x are their 0 slopes. And these points are called critical points. Critical points, while not always maxima or minima, will allow us to figure out for what horizontal value, and again, I'm trying to avoid using x because it doesn't have to be x, it could be with respect to time, any number of other variables, but we'll just keep it like that. So it'll help us determine the value of x at which a minimum or maximum occurs. A minimum or maximum can be either local or global. We'll come back to that in a moment. Now what I want you to see here is if we pick the point where we clearly see a minimum, and if I were to draw what I believe to be the tangent line at that point, notice that it would have a slope of 0. Okay? Because we're, in the context of the ride, at just that instant, we're neither traveling up nor are we moving downwards. We're basically level with the Earth. Okay, so what I would like to show you is this little applet. And this just allows us to see that as we move, changing the input value, as we change that input value, we can see that black line keeps up with the slope of the curve, right? You can actually kind of imagine that to be the cart moving as passengers are, coming down the ride and now level. Notice that right at x equals 0, we are completely level. We can zoom in on that. In fact, if I continue to zoom in at that point, notice that the red curve actually is flat or appears flat, especially in what we call a local area, a local region, or what we would call in the neighborhood of that critical point. We see that the red curve is essentially 0. So let me remove that black line, and you can actually see that's the bottom of the red curve, and we're not looking at it for a very large domain. We're from about negative 0.0001 all the way up to about 0.00015. So you can see that it really is the case that if you zoom in enough, you will see a horizontal line. If we take this and set it back to, let's say that point right there, so that's x equals 0.4, and if I zoom in really, really close, you can see the black line and the red curve start to converge into 1. In fact, now if I remove the black line, you'll notice that the red curve appears to be linear, and that's what we call local linearity. And the derivative allows us to figure out what the slope of that line would be if the function were approximated to be linear at that point. All right, so as far as the difference between local and global, let's recall for a moment by sketching a curve that'll have maybe several minima and maxima. Maybe it looks like this, and maybe that it comes back down, and then maybe it just flattens out. And then maybe this is just where we started. Okay, so the highest maximum would be what we call the global maximum. So here we have a global max. And then here we have another little max, right? Within a region, within an interval, we can see that this is actually a peak. And so this is what we call a local max. There's only going to be one global max if there's any global maxes at all. Let's say the function goes on to infinity, then there would be no global max. But there's only going to be, if there is a global max, it would be 1, and then every other little max, little peak will be considered local. Now, we'll just pretend that this flattens out here completely. So we have 2 local maxes, and we also have 2 local mins. We have one local min. This would be a local min. No, I'm sorry, we do have 2 local mins, because if we consider this the start of the function, then we could also call that a local min. And then down here we would have a global minimum because you can see that there are no other minima that fall below that one. All right, so this is the basics of a derivative and the concept of why we use it.